In this video, we're going to be talking about sampling variability and sampling distributions. Specifically, the sampling distribution of a sample mean. So let's go back to our fish pond at Wolf Creek. So suppose that there are only 5 fish in the pond. So that means that the lengths of the fish in inches are going to be given as 6.6, 11.7, 8.9, 2.2, and 9.8. Now, we're going to keep the population size small so that we can find all of the possible samples. So what is the mean and standard deviation for this population? So if we add up all those values and divide by 5, we're going to find that we have a mean of 7.84. When we calculate our standard deviation, we get 3.262. So let's find all of the samples of size 2. How many samples of size 2 are possible? We should have 10 total samples possible. So if we look at our pairs, and then from those pairs calculate each of their sample means, we get the following sample means. Now, all of these values determine the sampling distribution of our sample mean for the samples of size 2. What is the mean and standard deviation of these sample means? Go ahead and calculate that on your own now. So go ahead and push pause and calculate that. And then when you're done, push play, and let's see if you were right. So you should have gotten a sample mean of 7.84 and a standard deviation of the sample mean of 1.998. How did these values compare to the population mean and standard deviation? So now let's find all of the samples of size 3. How many samples of size 3 are possible? I want you to go ahead and calculate that, and then when you're done, push play, and let's see if you're right. So go ahead and push pause and calculate that. So you should have gotten 5, a combination of 5 taken 3 times, or in groups of 3, and it should have given you 10 samples. So here we have our triples, so each of our samples, and we've calculated each of their sample means. Now, these values here, so our samples, these values determine the sampling distribution of our sample mean for the samples of size 3. What is the mean and the standard deviation of these sample means? So I'm going to have you go ahead and calculate that on your own right now. So I'm going to push pause and calculate those, and then when you're done, push play, and let's see if you are correct. Calculating our sample mean, our mean of our sample means, we get 7.84, and our standard deviation of that sample mean is 1.332. So think about, how do these values compare to the population mean and the standard deviation? What do you notice? Did you notice that the mean of the sampling distribution equals the mean of the population? And that as the sample size increases, the standard deviation of the sampling distribution decreases? So there are some general properties of sampling distributions of the sample mean. Our first rule is that the mean of the sample means is equal to our mean of our population. The second rule is that our standard deviation of the sample mean can be calculated by taking the standard deviation and dividing it by the square root of n. Now this rule is exact if the population is infinite, and it is going to be approximately correct if the population is finite and no more than 10% of the population is included in the sample. Now, take a brief little note here that in the previous example, our fish pond examples, the standard deviation formula wasn't going to be correct because our sample sizes were more than 10% of the population. But we wanted to make sure that we were able to calculate all of those sample sizes. Let's look at another example. So the paper, Mean Platelet Volume in Patients with Metabolic Syndrome and its relationship with Coronary Artery Disease, includes data that suggests that the distribution of platelet volume of patients who do not have metabolic syndrome is approximately normal with a mean of 8.25 and a standard deviation of 0.75. So it looks something like this. Now we can use Minitab to generate random samples from this population. So we'll generate 500 random samples of size 5, and we're going to compute the sample mean for each. Now, similarly, we're also going to generate 500 random samples of size 10, 20, and 30. So the density histograms on this next slide are going to be the results of 500 sample means for each of those given sample sizes of 5, 10, 20, and 30. Now, what do you notice about the means of these histograms? What do you notice about the standard deviation of these histograms? What do you notice about the shape of these histograms? This leads us to our third rule. When the population distribution is normal, the sampling distribution of our sample mean is also normal for any sample size, as we see here. Let's look at again another example. So here the paper is the overtime period in an NHL game long enough, gave data on the time in minutes from the start of the game to the first goal scored for the 281 regular season games from the 2005-2006 season that went into overtime. And the density histogram for the data is shown here. Now, let's consider these 281 values as a population. So the distribution is strongly positively skewed with a mean of 13 and with a median of 10 minutes. Now, using Minitab again, we're going to generate 500 samples of the following sample sizes for this distribution. So size 5, 10, 20, and 30. Here's our distribution histograms. So these are our density histograms for those 500 samples. So we want to know, are these histograms in fact centered at approximately a mean of 13? What do you notice about the standard deviation of these histograms? And what do you notice about the shape of these histograms? This example leads us to our fourth rule on the central limit theorem. So when n is sufficiently large, the sampling distribution of the sample mean is well approximated by a normal curve, even when the population distribution is not itself normal, as we see here. So then we ask ourselves this question, okay, well, what exactly is sufficiently large? Like, how large is sufficiently large? And the central limit theorem can be safely applied as long as our sample size exceeds 30. Let's take a look at another example. So a soft drink bottler claims that on average, cans contain 12 ounces of soda. So we're going to let X denote the actual volume of soda in a randomly selected can. Now suppose that X is normally distributed with a standard deviation of 0.16 ounces. Now 16 cans are going to be randomly selected, and the soda volume is determined for each one. So we're going to let our X bar equal the resulting sample mean soda. It's important to make sure that we're defining that when we're working through a problem and trying to answer that. Now, if the bottler's claim is correct, then the sampling distribution of our sample means is going to be normally distributed with a mean equal to our population mean of 12 and a standard deviation of 0.04. So, what is the probability that the sample mean of the soda volume is between 11.96 ounces and 12.08 ounces? So we're looking for the area between those 2 points. Now, in order to get this, we're going to need a z-score. But in order to get a z-score, we need to standardize our endpoints. So to standardize these endpoints, we're going to use that the fact that our mean equals our sample mean, and that our standard deviation of our sample mean can be calculated by the standard deviation divided by the square root of n. So what that means is that we're going to take the 11.96 and subtract it from 12, and then divide that by 0.04. And this is going to give us our A star value, our left point, which is at -1. Now we're going to find our B star, which is for our right point. So we're going to take our 12.08, subtract 12, and divide by 0.04. That gives us a value of 2. Now, in order to get the z-scores for these, we're going to need to look them up in the table and then subtract the probabilities. When we subtract the probabilities, we need to take our B star minus our A star. So if we look our values up, we're going to get, for our B star, 0.9772, and for our A star, 0.1587. So we'll subtract our B star from our A star and get 0.8185. Now I want to take a quick second and kind of point out here that it's important that we're using our symbols correctly, because these things mean different things, right? And so we need to make sure that we're using appropriate symbols, because our p hat is different than our p, our sigma is different than our sigma sub x bar. So it's important to make sure as we're going through our problems and working through our problems that we're using the correct notation. Let's move on to one more example. So a hot dog manufacturer asserts that one of its brands of hot dogs has an average fat content of 18 grams per hot dog. Now, a standard deviation of 1 gram. So consumers of this brand would probably be pretty disturbed if the mean was less than, well, they probably would not be disturbed if the mean was less than 18 grams. But I bet they'd be pretty unhappy if it exceeded the 18 grams. So an independent testing organization is asked to analyze a random sample of 36 hot dogs. Now, suppose the resulting sample mean is 18.4 grams. Does this result suggest that the manufacturer's claim is incorrect? Now, since the sample size is greater than 30, our central limit theorem is going to apply here. So the distribution of our x bar, or of our sample mean, is approximately normal, with our mean equaling 18 and our standard deviation equaling 0.1667. So, suppose the resulting sample mean is 18.4 grams. Does this result suggest that the manufacturer's claim is incorrect? So we're looking for the probability that our sample mean is greater than or equal to 18.4. So the claim is that the mean is 18 and the standard deviation is 1. And when a random sample was pulled, the mean was 18.4. Now, using a sampling distribution, what is the probability that on average the sample mean will be 18.4 or greater? So we're going to calculate the z-score for that. So we're going to standardize it. So we have our 18.4 minus 18 divided by 0.1667, which gives us a value of 2.40. So now we can look that up in the table. But because we're looking for a value that is greater than or equal to, that's the right tail value. And our table only gives us the left side. So we'll need to take our number and subtract it from the number 1. So when we look up our 2.40 in the table, we're going to get a value of 0.1667. 0.9918. So we're going to take that and subtract it from the number 1, which is going to give us a value of 0.0082. So what does that mean? Well, that means that values of x at least as large as 18.4 would be observed only about 0.82% of the time. Now, the sample mean of 18.4 is large enough to cause us to doubt that the manufacturer's claim is correct. So this probability indicates that the manufacturer's claim is false. So the probability of a sample having this mean of 18.4 is very unlikely if 18 is the true mean.